Hello everybody, welcome to our first meetup of the year 2017. So let me start by wishing everybody a happy new year. I would also like to apologize for not going live this time because I realized that I have a flight later tonight and I need to leave to the airport earlier than usual. So I decided to record this video and share it with you guys so you can watch it at your convenience, either at 3 p.m. our usual time or anytime you like. So today, in our first meetup of the year, we are going to talk about self-assembly modular robotic systems. But first, what happened? Let me ask for your proposals because we want to hear from you. We want to hear about the cool projects that you're working on, about awesome research that you're doing, whether it's related to general robotics or evolutionary robotics or modular robotics, or not related to robotics, but it's related to artificial intelligence. Please send us your proposals, let us hear from you, and let's do this together. Our agenda for today will include definition of self-assembly, some systems including intelligent self-assembly systems, stochastically driven self-assembly system, whether it's 2D or 3D, planar distributed assembly model, and some self-assembly applications that we covered in our last meetup, but from a modular perspective. This time we will go through some of the systems that we discussed last time, but from a different point of view, which is more related to self-assembly algorithms. Okay, again, last meetup, before we start our new topic, let's remind ourselves about the last topic we talked about, which is modular robots. Modular robots are composed of various modules. Each module involves actuators, sensors, computational and communicational capabilities. Today, we're going to talk about one of the main benefits of modularity, which is self-assembly. Self-assembly process is ubiquitous in nature, as it generates much of the living cell functionality. However, it is uncommon in the technical field because it is considered as a new concept relatively in that arena, although it could help in lowering costs and improving versatility and robustness, which are the three promises of modular robotics. Again, low cost, versatility, robustness. The ability to form a larger, stronger robot using smaller modules allows self-assembled robots to perform tasks in remote and hazardous environments. In other words, self-assembly is the problem of designing a collection of elements with edge-binding properties, such that when they mix randomly, they bind to form desired assemblies. The elements may be homogeneous or heterogeneous. Their building properties may be fixed or dynamic, and may have a range of capabilities such as ability to detect binding events or exchange information with neighbors. Intelligent self-assembly systems were introduced by Jones and Matarik in 2003, and I'm not sure if I'm pronouncing the names right or wrong, but hopefully it's right. Anyways, the most important thing is the name of the system, which is Intelligent Self-Assembly System. With all respect to the authors Jones and Matarik, I hope it's right. The system was introduced in 2003. The system uses assembly agents and transition rule set compiler, which takes a goal shape as an input and gives a set of rules as an output that can be utilized by the assembly agents to assemble the target shape. When each assembly agent utilizes these rules, the desired goal structure is assembled. Each assembly agent has limited and local sensing and local rule-based control. The assembly agents can be equipped with increased computational capabilities. These increased capabilities may be utilized during the assembly process to allow for richer interaction and greater coordination among assembly agents or modules, in other words, in a simpler way, and therefore allow the assembly of more complex structures. However, each assembly agent remains an autonomous entity, limited to local sensing, with no pre-programmed action sequence and no pre-assigned location or task in the assembly of the final structure. Depending on the domain of the application, assembly agents may be modules, as we mentioned earlier. They could be called modules, which are, because we're covering actually modular robotics, so they should be modules in a modular robotic system. This algorithm can be incorporated into distributed reconfiguration algorithms for self-reconfigurable robots. Actually, we're going to cover self-reconfigurable robots in our next, in one of our next meetups. So we will talk about this system probably again. Stochastically driven self-assembly system. This system was studied by White and other authors in the year of 2004, as the group of authors developed algorithms and hardware for a few systems. One system uses square units with electromagnets that self-assembled into an L shape and then self-reconfigured into a line. How cool! The other system uses triangular units with swiveling permanent magnets that self-assembled into a line and then changed their sequence within the line. That's really cool. Both of these systems lack batteries, and the modules only receive power after they connect to the structure being self-assembled. A configuration map is distributed to each unit and allow locally determining which of its free bonding sites to activate in order to form a specific geometry. But this approach may lead to deadlocks. That's why an alternative to the previous approach is to temporarily moderate the formation such that cavities do not form through layered construction. Yeah. We always have problems. We should have problems in order to find solutions to solve these problems. That's why we're doing research. And that's why 2D always get extended to 3D. So the previous system, the stochastically driven self-assembly system, was extended from 2D to 3D by Tolley and other authors. The assembly algorithm takes place to plan the assembly of the fittest evolved robot by sampling a graph of all possible paths to the target structure and following those that leave the most options open. The input for this algorithm is a target function, and the output is a robotic structure. This is a little bit different than our first covered system, which is intelligent self-assembly system, which took an input a goal shape as an input and gave as an output a set of rules. Let me go to this slide. As you can see here, the input is a goal shape and the output is a set of rules. However, in this system, the input is a target function and the output is a robotic structure. So the robotic system will evolve using a frequency-based representation. And the assembly algorithm then takes place to plan the assembly of the fittest evolved robot by sampling a graph of all possible paths to the target structure and following those that leave the most options open. For each sample, the assembly problem is solved in a reverse order by beginning with the final structure and removing one valid module at a time to go backwards in order to guarantee the existence of a minimum of one path to complete final assembly at every assembly stage. However, the modules in this system are unable to move on their own, as they need to circulate in a turbulent fluid. That's a difficulty. But they solved it by using the fluid. The fluidic system could be scaled down to produce microscale modules. Interesting. So let's move on to planar distributed assembly model. It was proposed by Kelly and Zhang in 2006. In this system, homogeneous assembly agents or modules move randomly and asynchronously on a 2D grid of cells, attaching square blocks together to form a target structure, such that an agent can fit within one cell. Assembly starts with a seed block, and then the structure grows outwards from the seed. Assembly rules are stored in an internal lookup table, with each rule specifying a binding configuration that activates an assembly action. The group of assembly rules forms an assembly rule set that is identical for all agents in order to allow each agent of performing a complete assembly task if needed. Again, similar to the first system that we covered, which is the Intelligent Self-Assembly System by Jones and Matarik. The only difference is that the configuration for each assembly rule must be fully specified, and some small differences to allow assembling a large class of robotic structure. Do you guys see the similarity between this system and the previously mentioned system? Let me go through it again. This one, the Intelligent Self-Assembly System, and the Planar Distributed Assembly Model. If yes, please go to the discussion forum in the meetup group and write your comments. So let's go through some applications. Some of these systems, actually all of them, we covered them in our last meetup. I need to post a link to the last video, so if you didn't join our last webcast, you can go through the videos to learn more about these systems from a modularity perspective, because now we're going to talk about them from a self-assembly perspective. CBOT is a cellular robotic system that is capable of self-assembly. Assuming that a set of units, actually numerous sets of units, are connected in an arbitrary shape. First, a unit is chosen as the origin of the construction. This unit is called the kernel. Next, the kernel gathers adjacent units to compose a logical connection network according to the embedded plan. This network is the first stage. The units involved in the first stage network then gather some surrounding units and form the second stage network. Repeating this process increases the stages, and the network grows stage by stage, approaching the target configuration. In this method, a unit joining the network mimics the biological differentiation process. The units in the network are called differentiated, and others are called undifferentiated. The difficulty in construction is low due to using the layer approach, which acts as a kind of coordinated system to reduce the volume of search spaces. That's really cool. Fracta. The Fracta system is also capable of self-assembly, since each unit can connect to other units autonomously to form a given target shape through a diffusion-like process. Each fractum has the potential to become any part of the system and has information about the final shape of the whole system, so it can communicate with neighboring fracta in order to recognize the local connection and organize the whole shape accordingly. The function of self-assembly has been verified by computer simulation. Then this work was extended by Yoshida and other authors in 1999 to a 3D self-repair system. We're going to talk about self-repair systems probably next month, after going through self-reconfiguration systems. So stay tuned. So now we're going to talk about a system proposed by Chen and Burdick in 1995, where they tackled the problem of finding an optimal module assembly configuration for a specific task. They formulated the solution as a discrete optimization procedure based on assembly incidence matrix representation of a modular robot and a general task-oriented objective function that can incorporate many realistic task criteria. Genetic algorithms were employed to solve this optimization problem, and the canonical method to represent a modular assembly in terms of genetic strings was introduced. Modular robot assembly configuration was evaluated using a flexible and general assembly configuration evaluation function. However, in some instances, such a procedure will be computationally expensive. Instead, a discrete combinatorial optimization algorithm, which employs the modular robot evaluation function, is a desirable alternative because it's cheaper. In short, GA method is well suited for modular robot problem, especially when using the method to effectively encode modular robot assembly configurations in the bit strings required for the GA procedure. This system can be used with heterogeneous modular robots. All the previously mentioned systems can be used with homogeneous modular robots only. However, this system is different because it can be used with heterogeneous modular robots. Excuse me. Wintertime and coughing and problems. But let's not talk about them now. Let's talk about Samba, which is a mobile self-assembly modular robot that was implemented in 2010 by we and other authors. In this system, several modules can self-assemble to form a particular structure through an autonomous docking process that includes 4 phases: wandering, navigating, docking, and locking. The docking Samba, which is the active module, starts by wandering in a random path until a target has been found. Then the active module switches to navigation behavior and goes anti-clockwise around the target until it finds docking direction. It stops moving when the mechanical touch switch on the docking interface is pressed down. Then locking takes place when docking hooks lock tightly. After the active module confirms the connection with the target, the locking is accomplished. The resulting shape can reconfigure into different structures that are capable of various locomotion modes. We will obviously talk about Samba in our self-reconfiguration robotics webcast, probably in a week or 2. And you will see some cool locomotion modes that can be achieved using Samba. Last but not least, we have MBLOX. MBLOX is a cubic modular robotic system that is capable of self-assembly and self-reconfiguration. The MBLOX are independently mobile, and they show an ability to move through difficult environments. Although they only have a single actuator, they can exhibit several motions, including rolling, spinning in place, and jumping over obstacles. In order to drive an MBLOX towards a specific goal, a bimodal behavior was implemented. When the module's actuator is aligned with the goal location, the actuator is used to apply a moderate amount of torque that causes controlled rotation towards the goal. When the module is not aligned with the goal, the module is stochastically reoriented using a high torque, which causes unpredictable movement. A group of disjoint MBLOX executing this behavior can self-assemble into a lattice structure. That's it for today. I think we had a short webcast today compared to the previous 2 that we had last year, 2016. So it's time now for some Q&A, but because we're not going live, please go ahead and submit your questions, your ideas on the Meetup forum or the discussion forum underneath this Meetup. I'm going to post the link, and also I am going to post another link for our first hackathon. We are going to work with Kubelets in order to use their Kubelets modular robot, and we are going to do the first hackathon for building a self-assembly system using Kubelets. So if you're interested, please click on the link provided here to sign up for that hackathon that will take place probably in February of this year. Thank you for your time, and thanks for listening, and thanks for the questions that you're going to post. And have a wonderful rest of the day and rest of week. Thank you very much.